Hello everybody. This lecture is intended to provide information for completion of the individual SPC assignment, which is due at the end of week 5. The actual values and numbers for the individual assignment will be available in eCollege at the beginning of week 5, which is Monday at 12 a.m. In order to follow this along, please open your Beaux-Arts Quality PowerPoint Chapter 5, which is the one in front of you. And also this guy, I believe it's called the Problem Solving SPC page. These are all in doc sharing. These will help you as you go through your assignment. First, I'd like to put some definitions to quality. And I like this, the way this book did it that I used to use quite a while back, so I kept the slides. It talks about quality being characteristics of products or services. And they're not just characteristics, but it's those that bear on its ability to satisfy something, whether it's a stated or an implied need for a product or a service, and in some cases for people. So you can judge the value of people by the quality of their work. It's kind of the same thing. If you've had me in the past, you know that I think all this stuff's connected anyway. So I wanted to show that in this course, where we started out looking at financial value for a few weeks, and then we switched to quality to see how organizations show value in their products and services. So from the value perspective, this text gave a definition of quality as a perspective that holds that quality must be judged in part by how well the characteristics of a particular product or service align with the needs of a specific user, or in other terms, the way Deming or Duran would put it, how quality of your products or services align with the voice of your customer. Now the conformance perspective, which we'll delve into a little more this week, it's all about SPC, or statistical process control, and that's when you're focused not on the product or service, but did it do its job? Was it made correctly? How was the processing? How were the systems involved? That's the whole conformance perspective of it. It gives you 8 dimensions of quality. We're going to really look at the control of these before they even leave your organization, before they get to the customer. They do use statistical process control to look at durability and reliability and conformance to specifications, and that's what we're going to look at today. The total cost of quality is something that came up in the 70s and 80s. I know that it hit its stride in the mid to late 80s when they were talking about total quality programs and quality circles and things like that, where they measured how much defects cost in your system, and they broke it up into 4 basic groups: prevention, cost, appraisal, and then internal and external failures, which we talked a little bit about in our last little lecture. Total quality management, like I said, came about in great popularity in the 80s, and it's even used today, where the organization tries to show through quality measures like the one we're going to do today that their products are of higher value than their competitors' products, and they can show this through the use of statistics or measurements or other metrics that they come up with. It has a customer focus because they always look for the voice of the customer, or what the customer is really looking for. They're always trying to continuously improve their process and systems. They're getting leaders involved. So those are some of the tenets of it, and like I say, it's even used today. But here's the question: can the process that you're using to produce your product or service provide acceptable quality, that's the value customers put on it, consistently each and every time you deliver that product or service? Is it going to be consistent and have repeatable value every time a customer calls on it? That's really what you're trying to answer, and that's why we use statistical process control. The main ratio that we look at for process capability, just to see if your process is even capable of producing a valued product, is called the CP index, and that's just a process capability ratio. Like it says, it measures whether or not it's potentially capable of meeting the quality standards set up by you and your customer. Now you'll see on these the upper tolerance limit and the lower tolerance limit are the actual contractual limits put forth by you and your customer. They're agreed upon that these are the limits your product's going to fall within. They're typically measurements. And then you divide that by 6 standard deviations of your process, and that gives you whether or not your process is capable. And we'll get into all that in a minute. Don't let the formulas scare you in any of this. Like I used to tell people we trained on the shop floor that saw numbers and got kind of nervous right off the bat. If you can add 5 numbers and divide by 5, you can do anything I'm going to ask you to do. Well, this is really what you're going to be looking at. This is called a normal distribution. And if you just took measurements off of parts and started plotting points on a graph or a scale, you'd have all kind of points, and typically if you drew a line around it, this is what it looked like if it was in a normally distributed population of measurements. Now, outside of the CP, a thing that we can do to see how well your system or your process stays within the limits, we measure something called process capability, or CPK, and that's whether or not a process is capable of meeting certain quality standards and is centered between the spec limits. And once again, don't get excited about the formula. We'll go through and make this a little easier in a minute. Six Sigma's big buzzword the last 10-15 years. This really came out of the stuff that Schuhart and Deming and Duran were doing back in the 40s. And it's just a way to prove that your process is in control. So you're really looking for something plus or minus 3 standard deviations. That's what the -6 and the +6 are. They've extended that. It used to be 3, now it's 6. You're talking about parts per million defective versus parts per billion defective. And that's what we're striving for when we continuously improve our products and process. One of the ways we measure this, and I've seen this done in hospitals and manufacturing and sales offices all over, is we use control charts. And that's a simple chart that you can use to show that your process is consistent and capable over time. And we typically, what we're going to look at in our individual assignment is look at variable information, not just attribute whether it's good or bad. We're going to look at variable information that changes with each measurement. Sampling is something we do because we don't. It's not cost efficient to measure every single part that comes out of our process, or measure every single service that we do. We've shown that it's statistically significant. If we do a sampling of it, you get about the same results. Typically we use 4 or 5 in a sample. For this example, I believe they use 5, and for the one we're going to do, we're going to use 5 also. So what we come up with are things called sample average, or X bar. See, it has a little bar over it, and that just shows the central tendency of that subgroup or that sample that you did. And the other little nomenclature that you need to get used to is range, or R, and that shows the variation in the sample group. And all range is the highest measurement minus the lowest measurement of that sample. The control charts we plug these numbers into after we do a little manipulation is called an X bar and R chart, where we're typically measuring the averages and the ranges throughout the chart. We're not going to do the P charts or attribute charts in this little lesson or our assignment, so don't worry about those right now. This is typically what you'd find if you did 10 samples of 5 samples each. You did 5 measurements each. You can see them across the top here. Your sample 1, here are your 5 measurements. Now, in order to do this correctly, you need a very simple calculator, either on your phone or a handheld calculator. And what you do is, for sample 1, let's say, you would add up 136, 137, 144, 141, and 138, and then you would divide by 5 because that's how many parts were in that sample, and you'd get an average reading. So take some time and do that. You might want to pause this and see if you can get the average for each one of these 10 samples, because in the next little slide it kind of shows you what they are. So if you added up all 5 readings in sample 1 and divided by 5, your X bar or average would be 139.2. Same thing for number 2 would be 140, and so on until you get all 10. Now for the ranges for each, let's go back to this. The highest value is 144. The lowest value is 136. So that difference, highest minus the lowest, is 8. So there's your range for the first one is 8. Highest minus the lowest in sample 2 is 5, and then 9, and so on and so on and so on. Alright, so you use these as building blocks to construct your control limit so we can make some charts. And what you have to do to get your X double bar, that's all this one is over here, is you take the X bar or the average for sample 1, add it to the average for sample 2, and so on until you add all these averages together, all 10 of them, and then you would divide by 10 and you get 139.8. Same thing for the ranges. If you want your R bar or your average range, you'd add up all the ranges, divide by 10, and you get 5.3. Now those are useful because we want to figure out what our control limits are, so we can start measuring future sample readings and see if we're in control or not. And these are the formulas for the various control charts. This is for the upper control limit on a range chart. You take the D4 value, which is on this page, a D4 value with a sample size of 5 is 2.11. So 2.11 times a 5.3, now where'd 5.3 come from? That was our average range. Added all these up, divided by 10. So 2.11 times 5.3, we get our upper control limit of our range chart of 11.2. The lower control limit of a range chart, typically if you're doing a sample size of 5, is 0, so don't worry about that. Really just follow the upper limit. Now we do the same thing for our X bar and our average control chart. Our upper limit would be our grand average, which was 139.8, plus the A2 value, right there, sample size of 5.58 is our A2 value, times the average range, which was 5.3. We used it in the last calculation, and you do all this math. You times these two first, and then you add it to that, and you get their upper control limit for your X bar chart at 142.9. Now you do pretty much the same thing for your lower control limit, but instead of adding this, you just subtract it. So you take the 139.8, you take your A2 times your R bar, but instead of adding it to 139.8, you subtract it from 139.8, and you get 136.7, which is your new lower control limit. Now if you were to graph these out and plot the next couple samples you had, and you had in sample 11 out of the 5 pieces, you had an average of 141.2, you'd plot that on here, and there it is. And you'll see after so many plots you get an average of 144. It's in 13, and now you're outside the limits. And what that tells you is you need to do something to get your process back into control. And that's what the customers want to see. They want to see that you actually recognize your process was out of control and that you did something to get it back into control, which usually this shows you did something here so that it got back more towards the center line or the grand average or X double bar line.